In this section 3.1b, we're going to focus on interpreting the correlation, which you'll see how to find that today. You'll understand the basic properties of correlation, including how the correlation is influenced by outliers. We'll use technology to calculate correlation, and we're going to explain why association does not imply causation. So remember, a scatter plot displays the strength, direction, and form of the relationship between two quantitative variables. Linear relationships are important because a straight line is a simple pattern that's quite common. Unfortunately, our eyes are not good judges of how strong a linear relationship is. A correlation R measures the direction and strength of the linear relationship between two quantitative variables. R is always some number between -1 and 1. R greater than 0 indicates a positive association. R less than 0 indicates a negative association. And values of R near 0 indicate a very weak linear relationship. The strength of the linear relationship increases as R moves away from 0 towards -1 or 1. So the bigger the number, the stronger the correlation. So if you look at these examples of linear association occur only in the case corresponding of a correlation. Linear relationship. This first graph shows a correlation of 0. They're really just a big blob. There's no linear pattern to it. This one shows a correlation of -0.3. It's definitely going down, but the numbers, the points, the data points are not in a very good straight line. If you look at this one, we're going up, so we're positive, and we're starting to get more linear than what we had in this second graph, but we still have a correlation of 0.5. So it's kind of linear, but the points are still a little bit scattered. Notice -0.7, we're starting to get a better shape. If we draw this line here, we can see that it's pretty good. We have some points all around that line. And then a correlation of +0.9, positive slope, and then a negative correlation of -0.99, almost linear. So those are some ways that you can look at the different correlations and determine what the correlation value should be. So the formula R is a bit complex, but it helps us to see what correlation is. In practice, you should use your calculator software or software to find R though. So I'm just going to show you this. You don't have to do this ever. I'm not going to force you to. And we'll look at how we find the correlation. Some facts about correlation. How correlation behaves is more important than the details of the formula. Here are some important facts about R. Correlation makes no distinction between explanatory and response variables. So the correlation does not determine between the two, and it doesn't matter if you mess those up. R does not change when we change the units of measurement for both X, Y, or both of them. So your R is not going to change. Your correlation won't change if you change the units. Correlation R itself has no unit of measure, so correlation has no units. And things to be aware. Correlation requires that both variables be quantitative. Correlation does not describe curve relationships between variables, no matter how strong the relationship is. Correlation R and interpret in context. So we have correlation is not resistant. R is strongly affected by a few outlying observations. And correlation is not a complete summary of two variable data. This one still looks a little positive, but not too linear. This one to me doesn't look very good at all, so closer to 0. And this one's slightly negative, but we have these outliers over here that are going to make it so it's not hopefully a big correlation. You'll do those. You'll look at that. Those graphs are also in your book on page 153. I want you to come up with what you think the corresponding correlation would be. We'll talk more later about how to find the correlation in the calculator.